So today's topic is advanced number theory. So normally we start with the problem of the week, but actually this week's problem of the week had more to do with today's topics. We're actually going to talk about it halfway through the class. So that's a bit different about today's class. Other than that, let's just get straight into today's topic. So the first thing we're going to do is quadratic residues. So some of you may not know what quadratic residues are. So to motivate them, first, note that when we're working with natural numbers, it's really easy to tell if a number is square. Just check if it's a perfect square. But the same is not true when we're working mod n, for example. Just as a simple example, for example, if we have 3 is obviously not a square. But when we take it mod 11, for example, 3 is actually 5 squared. So now 3 is a square mod 11. So this motivates us to define basically the squares inside a certain modular class. And it can actually be really useful to know whether or not we can take the square root of a number give in a certain mod. So we give these squares per se a special name, namely quadratic residues. So to formalize our definition, a quadratic residue mod p is a number a such that there exists some integer x such that x squared is equivalent to a mod p. So are there any questions with this definition? Or can we move on? Okay, great. So the first thing we're going to do is prove some interesting properties of quadratic residues. So the first thing we're going to do is prove that the number of quadratic residues in a certain mod p is actually exactly p plus 1 over 2. So does anybody have any ideas on how to do this? Yeah, so we learned about orders last week. We can definitely use them for this proof. In particular, the order of a quadratic residue, actually, the only condition is that its V2 is less than that of P minus 1. But we're actually not going to do it that way. We're going to use a much simpler technique. So let's begin by squaring every single residue mod P. So basically, we just need to find when two squares intersect. So how can we do that? When do we have, for example, x squared is equivalent to y squared mod P? Well, if x squared is equivalent to y squared mod P, we can move y squared over and factor to get x minus y times x plus y is equivalent to 0 mod P. So P is a prime, so the only way for this to be true is if P divides one of them. We know that P can't divide x minus y because x and y are distinct. So P has to divide x plus y. So in fact, two squares can only coincide if they correspond to negatives of each other mod P. And this is an if and only if. If they're negatives of each other mod P, then their squares are the same. So if we square every single number, every single one of the P residues, we get the quadratic residue 0. And for the remaining P minus 1 residues, they can be put into pairs, negative pairs. So like 1 gets paired with -1, 2 gets paired with -2, and so forth. So though we get P minus 1 non-zero quadratic residues from squaring them all, they pair with each other to only form P minus 1 over 2 distinct residues. So adding 0, this makes exactly P plus 1 over 2 quadratic residues. So does this proof make sense? Great. So let's go ahead and move on then. So before we get to any other properties, we're going to define a very useful notation called the Legendre symbol. So this is just a way of rewriting whether or not a number is a quadratic residue. So the Legendre symbol is denoted A over P in brackets. So don't mistake this with division. It's sometimes ambiguous, but generally it's pretty clear because the Legendre symbol always has parentheses around it. So we define A over P to be 1 if A is not 0 mod P and A is a quadratic residue. We define it to be 0 if it is 0 mod P and -1 if it's a non-residue. So from what we had before, this means that A over P is actually 1, P minus 1 over 2 of the time, -1, P minus 1 over 2 of the time, and 0 only once, exactly when A is 0. So this is just definition, but it's actually going to help us a lot. In particular, we can actually find a closed form for the Legendre symbol. So the formula for finding the closed form for the Legendre symbol is called Euler's criterion. So some of you probably have seen this before, but in case you haven't, it states that the Legendre symbol x over p is equivalent to x to the p minus 1 over 2 for every single x. So this is not that hard. I'll just go ahead and prove it. So the result is obvious for x equals 0. And for non-zero x, remember we learned last week that we can always write x is equal to zeta to the k, where zeta is some primitive root, and k is some number less than p minus 1. So now we have that x to the p minus 1 over 2 is zeta to the k times p minus 1 over 2 by exponent properties. And the exponent, we can take mod p minus 1 by Fermat's little theorem. So the exponent is p minus 1 over 2 mod p minus 1 if k is odd, and it's 0 otherwise, because then it's divisible by p minus 1. And we know that if the exponent is p minus 1 over 2, then zeta to the p minus 1 over 2 is just -1. And zeta to the p minus 1 is, of course, 1 by FLT. So the right-hand side is -1 if 2 does not divide k, and 1 if 2 divides k. Does that make sense? Let me know in the chat if I need to go slower. Okay, so I guess I'll repeat the last bullet. So remember, we're letting k be the unique number less than p minus 1 such that we can write x is equal to zeta to the k. So the right-hand side of our expression is zeta to the k times p minus 1 over 2, since we're just raising x to the p minus 1 over 2. So when k varies, we only have to take the exponent mod p minus 1, since we know zeta to the p minus 1 is 1. So it's p minus 1 over 2 mod p minus 1 if k is odd, and it's 0 otherwise. Does that part make sense? Here we're just using FLT. So now, once we have this, we know that zeta to the p minus 1 has to be 1. So the right-hand side is 1 if 2 divides k. And zeta to the p minus 1 over 2 is -1, because it's the square root of 1, and it can't be +1 because zeta is a primitive root, so it's -1. So we have the right-hand side is 1 if 2 divides k, -1 otherwise. So how about the left-hand side? If k is even, then x is obviously a quadratic residue, since it's just a square of zeta to the k over 2. And if k is odd, let's suppose the contrary, namely that x is equal to y squared. And of course, y can also be expressed in terms of zeta. It's zeta to the j for some j. And what does this give? We know that x is equal to y, well, x is equivalent to y squared. So this tells us that zeta to the k is equivalent to zeta to the 2j, which means that zeta to the k minus 2j is equivalent to 1 mod p. And why is this impossible? Yeah, so we already said that k is odd, but since zeta is a primitive root and this is equivalent to 1, we should have p minus 1 divides k minus 2j. But p minus 1 is even, so if this is true, as people have said in the chat, that means k has to be even too. So that's impossible. Therefore, y does not exist, and x has to be an NQR. This is abbreviation for non-quadratic residue. So both sides are 1 if and only if k is even, and both sides are -1 if and only if k is odd, as desired. So is this making sense so far? Okay, we'll take that as a yes. So using this, we can now prove a very non-intuitive corollary, namely that the Legendre symbol is multiplicative. So A over P times B over P is equal to AB over P. And using Euler's criterion, the proof is really easy. So we just plug in A and B into Euler's criterion. And A to the P minus 1 over 2 times B to the P minus 1 over 2 is equal to AB to the P minus 1 over 2. So it's really just easy to see this with the criterion, but it's actually really non-trivial because this tells us, for example, that the product of two quadratic residues is a quadratic residue. Maybe that's not surprising, and neither is the product of a quadratic residue and a non-quadratic residue is a non-quadratic residue. But what this tells us, which is really cool, is that the product of any two non-quadratic residues is actually a quadratic residue. And we'll see that the multiplicativity of the Legendre symbol ends up being extremely useful when we actually apply it to questions. But we'll move on. And after this, we're going to prove one of the most celebrated results regarding quadratic residues, which is called quadratic reciprocity. So this is going to be a very hard, very involved proof. So just tell me in the chat whenever I need to slow down. But let's get started then. So first of all, here's a statement. I'll give you a moment to digest it. So for distinct odd primes P and Q, we have that P over Q times Q over P is equal to -1 to the 1/4 times P minus 1 times Q minus 1. And the reason this might be surprising is, though we know a lot about the structure of Legendre symbols when the denominator is the same, this actually gives us a way to flip the denominator to the top. So we have a way to relate P over Q and Q over P. And this proves very useful in finding the quadratic residues of really large primes, because we can just continue flipping until P is very small. This will make more sense in a later example. But for now, does anybody have any questions about the problem statement itself? Okay, well then let's move on to the proof. So be sure to copy this down. The problem statement's only going to be on this slide. So before attempting to prove quadratic reciprocity, we're going to begin with a lemma known as Eisenstein's lemma. So Eisenstein's lemma states that given odd primes P and Q, we have this relationship. So Q over P is equal to -1 to the power of the sum of the floor of QU over P, where U ranges over all even non-zero residues. So U can be 2, 4, 6, 8, all the way to P minus 1. So does anybody have any ideas on how to prove this? Yes, we are going to be using Euler's criterion at some point. So yeah, that's something good to note. The left-hand side is just -1 to the q minus 1. I mean, it's going to be q to the p minus 1 over 2. So let's keep that in the back of our minds. We somehow want to get a q to the p minus 1 over 2 on the right-hand side. So to start out the proof, we are going to define R of u to be the remainder when QU is divided by P. So this is just normal remainder, and we're going to define it over all even U between 0 and P. So first of all, can we say anything about the quantity -1 to the RU times RU for any U? No, it doesn't have to be positive because RU doesn't have to be even. Yeah, it's distinct over all U. That's true. Can we say something about its parity? So when RU is even, -1 to the RU times RU is positive. And when it's odd, it's negative. But if it's odd, its residue is actually P minus RU, right? Because uh, we define the residue to be positive. So actually, either way, the residue of -1 to the RU times RU has to be even. Because if it's RU is even, we have that the residue is RU. And if RU is odd, its residue is P minus RU. Either way, it's even. And as Max said in the chat, we also have that RU is distinct over all U. So the answer to this question is no. And the reason why is, okay, let me give a moment for you guys to copy down everything on this slide. Okay, and yeah, the reason why it's distinct is that if we have -1 to the RU times RU is equivalent to -1 to the RV times RV for different U and V, then we have to have RU is equivalent to plus or minus RV mod P. Remember, RU is equivalent to QU, RV is equivalent to QV. So this means that Q times U plus or minus V is equivalent to 0 mod P. And since U and V are distinct, we can't have U minus V is equivalent to 0. So we need U plus V is equivalent to 0. So U plus V is equal to P, but U and V are both even and P is odd. So this is impossible, and we have that -1 to the RU times RU is distinct over all U. Does that make sense? Okay, so which part doesn't make sense? So I'll go over, so the reason why U plus or minus V can't be 0 is that we assume that U and V were distinct. So U minus V can't be 0. On the other hand, if U plus V is equivalent to 0 mod P, that means it's a multiple of P. But U and V are both less than P since they're residues. So this tells us that U plus V is less than 2P, which means that U plus V has to be P, and that fails by parity. Okay, the last part of the last slide. I was just stating the last bullet. So the last bullet is just supposing that if two of them were equal, and then we find the contradiction on the next slide. Okay, so now we have that u plus v, now we have that all the residues are distinct, and we also have that all the residues are even. So what does this tell us? Well, remember u cycles over all the even residues mod p. And since there's exactly p minus 1 over 2 of them, that means that negative 1 to the ru times ru achieves p minus 1 over 2 distinct residues. And since it's always even, it actually achieves every single even residue. So the set negative 1 to the ru times ru is just a permutation of the even residues. So this means that if we take the product of all the negative 1 to the ru times ru's, we'll just get the product of all the even residues. The product of all the even residues is the product over u of u, since u is an even residue. And the product over this is negative 1 to the ru times ru. And we'll factor out the negative 1 to the ru on the outside. And we remember that ru is actually just is equivalent to qu. So the right-hand side is negative 1 to the sum of ru times the product over all u of q times u. Does that make sense? So given this relation, what can we get? So we see that the product of over all u on both sides appear on both sides. So we can cancel them out to get the left-hand side becomes 1, and the right-hand side becomes q to the p minus 1 over 2 times negative 1 to the sum of ru. And the reason why q is raised to the power of p minus 1 over 2 is because it's multiplied p minus 1 over 2 times, because that's how many even residues there are. And as we stated much earlier, q to the p minus 1 over 2 is just q over p, the Legendre symbol of q. So since we have that 1 is equivalent to this, and both of them are plus or minus 1, q over p is just equal to negative 1 to the sum of ru. So does that make sense? Okay, so now we have q over p is equal to negative 1 to the sum of ru. But remember, this isn't the form we want. What we want is that the sum at the top is actually floor of qu over p. So there's still work to be done. So how can we relate ru with the floor of qu over p? Remember that ru is the residue of qu mod p. Yeah, RU over P is the fractional part of QU over P. So using this, we can write a relation. The floor of QU over P is equal to QU minus RU all over P. So RU is equal to P times the floor minus QU, just by rearranging terms. So now this is nice because U we defined was even. So QU is an even constant, is an even number, and P is odd. So RU is actually equivalent to floor of QU over P mod 2. And all we need is for them to be equivalent to mod 2 because we're ending up raising the sum to, it's the power of -1. So we only care about its parity. So since we knew that the Legendre symbol at Q is equal to -1 to the sum of RU, and we know that the parities are equal, we actually have that's also equal to -1 to the sum of QU over P as desired. And that finishes Eisenstein criterion. Does that make sense? Yeah, this entire proof was just to prove Eisenstein's lemma. But actually Eisenstein's lemma is very, very important to our proof, and we're actually basically done now. But first, we have to note that Eisenstein's lemma, though it's really nice, it gives us a nice way to express Q over P, is not that great because U ranges over even residues. And that's not easy to work with. We want to somehow convert U to range over all residues. So we need to find a way to make this expression simpler. So the way we do this is with another claim. I claim that this expression is true. So on the left-hand side, I have our current sum. We have the sum over all even residues of floor of QU over P. And I claim that this is equivalent mod 2 to the sum from I equals 1 to P minus 1 over 2 of floor of QI over P. So does everyone see why the right-hand side is much nicer? It only goes up to P minus 1 over 2, but this time we actually don't skip any residues, which means that the sum is much more well-behaved. So let's go ahead and prove this. So first of all, if we take a random U, we have that the floor of QU over P plus the floor of Q times P minus U over P is equal to QU minus the residue of QU over P plus Q times P minus U minus its residue all over P. This is just the exact same thing we used before. The floor is equal to QU minus its, is equal to X minus its residue all over P. So can anybody tell me something about the sum of the two residues? No, R is a function. R is the residue of its argument. So, well, not exactly. So remember, residue is always between 0 and P. So what we have here is R of QU plus R of Q times P minus U. So now we know that QU and Q times P minus U are negatives mod P. So the remainders have to add to P since none of P divides neither of them, right? Since the remainders are positive and the sum of the remainders is between 0 and 2p and is divisible by p. So using this, we have that the sum of the floors is equal to qu plus q times p minus u minus p, which is the sum of the residues all over p. And simplifying, this is q minus 1. So since q minus 1 is even, this means that the floor of qu over p and the floor of q times p minus u over p have the same parity. So can anybody see how this would prove our claim? So basically we're going to try to find some sort of bijection. So remember we're the left-hand side sums over all even p, all even u, but p minus u, since u is even, p minus u is odd. So if we find a bijection, we can actually take only some of the evens and turn them into odds to get the range from I equals 1 to p minus 1 over 2. And this is actually pretty easy. So what we're going to do is we're going to split our sum based on if u is less than p over 2 or if it's greater than p over 2. And if it's less than p over 2, we keep q times u. And if it's greater than p over 2, we change it to p minus u. And this is fine since, as we just proven, these two sums actually are the same mod 2. And what's the second sum? Well, as I just said, u is greater than p over 2, and 2 divides u, which means that p minus u is less than p over 2 and is not divisible by 2. So the right-hand side, the right sum actually adds floor of qu over p over all odd numbers less than p over 2. So if we combine the two sums again, it's just the sum of u is less than p over 2, and either 2 divides u, in which case is counted in the first sum, or 2 does not divide u, in which case is counted in the second sum. And of course, all numbers are either even or odd. So this sum is just the sum from u equals 1 to p minus 1 over 2 of floor of qu over p, as desired. So using this claim, we can convert Eisenstein's lemma, which is useful for bulky, into a much simpler representation. Namely, the Legendre symbol at q is equal to -1 to the sum we just wrote, from u equals 1 to p minus 1 over 2 of floor of qu over p. So remember what we sought to prove. We sought to prove quadratic reciprocity, which stated that q over p times p over q is equal to -1 to the p minus 1 times q minus 1 all over 4. So we have a way to express q over p as a power of -1. And likewise, we can flip p and q to find a similar expression for p over q. So it would be really nice if the two exponents on the left-hand side and the right-hand side were equal. Namely, the sum from u equals 1 to p minus 1 over 2 of floor of qu over p, plus the same thing when q and p are reversed, is equal to p minus 1 times q minus 1 over 4. This would prove the result, as now both sides are -1 raised to the same power. And actually, this identity is true. So just as a bonus, can anybody see why this is without writing anything down? Yep. So as Max said in the chat, it's actually double counting the number of lattice points in a p minus 1 over 2 by q minus 1 over 2 rectangle. So in case you guys don't see this, so consider the rectangle in the coordinate plane bounded by the lines x equals 0 and p over 2, and the lines y equals 0 and q over 2. So what does the first sum count? Well, what's floor of qu over p? Floor of qu over p counts the number of lattice points with x coordinate u, which are under the line y equals q over px. And since we're summing over all u between 1 and p minus 1 over 2, the first sum is going to count the number of lattice points inside the rectangle we just drew under the line y equals p over qx. Okay, somebody asked if we could scroll up. Okay. So, let me know when we're okay to move on. Okay, great. So as I was saying, floor of q over p counts the number of lattice points with the x coordinate u under the line y equals q over px. So the first sum is going to count the number of lattice points in the rectangle under y equals p over, that's supposed to say q over px, not p over qx. That's a typo. And likewise, if we consider the floor of pu over q, this counts the number of lattice points with y coordinate u, which are to the left of the line x equals p over qy. And if we think about it, this is actually the same region as the lattice points above the line y equals q over px. If we just rephrase it in terms of x coordinates instead of y coordinates. So one sum counts the number of lattice points below the line, one sum counts the number of lattice points above the line. But what about lattice points on the line? Well, since q and p are co-prime, they're both primes, there actually are no lattice points on the line. So the two sums just count the number of lattice points in the rectangle as a whole. And the rectangle is a p minus 1 over 2 by q minus 1 over 2 rectangle. So the sum of the two sums is p minus 1 over 2 times q minus 1 over 2, which is exactly what we wanted. It's p minus 1 times q minus 1 over 4. So we're done, and this proves quadratic reciprocity. So this was a really long proof. Are there any questions at all? If not, we're going to move on to our first application of quadratic residues today. And it's actually the problem of the week. So if you haven't read the question, take a moment now to do so. And feel free to type any ideas in the chat. Okay, so probably the first thing we want to do in this question is to find Q. So obviously P and Q are two disjoint parts of the question. So let's find Q first. And how can we rewrite the function f to make this easier? Yeah, we're going to complete the square. So f is a quadratic. We complete the square to get x plus 5 over 2 squared minus 13 over 4. And why is this nice? Well, x plus 5 over 2 is going to range over all residues. So this means x plus 5 over 2 squared ranges over all quadratic residues. So the number of values f of x can attain is actually just the number of quadratic residues. And we already showed earlier that that's p plus 1 over 2. So Q is equal to 1009. Now let's deal with P. So we're going to actually use the same form when we complete the square. So note that P doesn't include n equals 0. So we're going to define R to include n equals 0 since it's actually slightly easier to solve for. So R is equal to the product from n equals 0 to 2016 of n plus 5 over 2 squared minus 13 over 4. So let's reindex it to get the product from n equals 0 to 2016 of n squared minus 13 over 4. So first of all, how many times does each quadratic residue appear in this product? Well, as we said earlier, when we square every residue, 0 appears once and every other quadratic residue appears twice. So what I mean by reindexing is that right now, let me go back to the previous slide. So in the previous slide, we had n plus 5 over 2 squared. So like we could proceed from here, but like we just take an extra step, we reindex it such that, let's say we take an index I such that I is equal to n plus 5 over 2. So now I is still going to range between 0 and 2016. Since ranging between 0 and 2016 is the same as ranging between 5 over 2 and 2016 plus 5 over 2. But it's unnecessary since anyways we're going to reduce the question to quadratic residues now. So note that each quadratic residue appears twice besides 0. So we first move n equals 0 out, that's negative 13 over 4. And every other quadratic residue appears twice. So we can write it as the product of n minus 13 over 4, where n is a non-quadratic residue. I mean, n is a non-zero quadratic residue. And then we square the result. And just for simplicity, I'm going to rewrite as 13 over 4 minus n. Just take a negative. And it doesn't matter since we're squaring. So how can we find the inner thing? Well, the inner function looks kind of like a polynomial with quadratic residues as its roots. And then we evaluate it at 13 over 4. So it'd be really nice if we had a polynomial p with roots, which are exactly the quadratic residues. That way we would have that r is equal to negative 13 over 4 times p of 13 over 4 squared. So does anybody have any guesses for what p is? Yeah, x to the 1008 minus 1. And the reason why is by Euler's criterion. Remember that a quadratic number is a quadratic residue if and only if we have that x to the p minus 1 over 2 is equivalent to 1 mod p, or equivalently x to the p minus 1 over 2 minus 1 is equivalent to 0. And this polynomial x to the 1008 minus 1 has degree 1008, so it has at most 1008 roots, and we already know its roots are the quadratic residues, and so these are exactly its roots. So actually x to the 1008 minus 1 is exactly the polynomial we're looking for. So when we plug p into it, we're going to get, when we plug 13 over 4 into it, we're going to get that r is equal to negative 13 over 4 times the Legendre symbol evaluated at 13 over 4 minus 1 all squared. So what can this be? This inner term is either going to be 0 or negative 2, depending on what the Legendre symbol evaluates to. So how can we find the Legendre symbol at 13 over 4? Well, it's a job for quadratic reciprocity. So first of all, 13 over 4 over 2017 is equal to 13 over 2017, since 1/4 is a perfect square, and we just use multiplicity. So to find the quadratic, to find 13 over 2017, we use quadratic reciprocity. 13 over 2017 times 2017 over 13 is equal to negative 1 to the power of 12 times 2016 over 4, which is obviously 1. So that means that 13 over 2017 is equal to 2017 over 13. And the residue of 2017 mod 13 is 2. So this is just 2 over 13. And it's very easy to check that 2 is actually a quadratic non-residue mod 13. So 2 over 13 is negative 1, which means that 13 over 2017 is also negative 1 by quadratic reciprocity. So given this, we just plug it back in, and we get that r is equal to negative 13 over 4 times the negative 2 squared, which is equal to negative 13. Putting this all together, remember that we have r is equal to f of 0 times p. We multiply by f of 0. F is x squared plus 5x plus 3, so f of 0 is 3. So r is equal to 3p, and p is equal to negative 13 over 3, which comes out to 668 mod 2017. So p is 668, and q was 1009, and our answer is 12. So this is the solution to the problem of the week. Are there any questions? This solution will not be on the handout, but it's going to be on the transcript. So you can read it after class if you still have any questions, but feel free to ask them here if you do. Well, looks like there are no questions, so we're going to move on to our next QR application. So this is a pretty famous question. I'll give you a few moments to read it. Find the number of ordered pairs, x and y, such that x squared plus y squared is equivalent to 1 mod 2027. And it may be helpful to know that 2027 is prime. So does anybody have any ideas on how to do this? Yeah, I said that 2027 is prime. So I guess let's get going on this question. The first thing we probably want to do is to see how many solutions for x are there for a fixed y. So we want that x squared is equivalent to 1 minus y squared. So given this fixed y, how many solutions are there for x? Well, this depends on if 1 minus y squared is a quadratic residue. In particular, if 1 minus y squared is equal to 0, then x has to be 0. So there's one solution. If 1 minus y squared is a non-zero quadratic residue, then there are two solutions for x, since it can be square root and negative square root. And finally, if it's a non-quadratic residue, there's going to be 0 solutions, because we need 1 minus y squared to be x squared. So what do these numbers remind you of? Yeah, they look like the Legendre symbol, but we're adding 1. So as Aaron said in the chat, these numbers correspond to 1 minus y squared over p plus 1, where p is equal to 2027. So now we can write the number of total solutions as the sum from y equals 0 to 2026 of 1 minus y squared over p plus 1. And we're just going to move all the plus 1s out as well as y equals 0. So this becomes the sum from y equals 1 to 2026 of 1 minus y squared over p, and then we just add 2028. So how can we deal with the sum on the right-hand side? Well, in general, sums like these are really hard to deal with. So for this question, we're going to use a special trick. We're going to substitute 1 over y for y. So note that when we replace y with 1 over y, this is a bijection since 2027 is prime. So this means that 1, 1/2, 1/3, all the way to 1 over 2026 is actually just a permutation of the numbers 1, 2, 3, all the way to 2026. So if we do this, we can rewrite s as the sum from y equals 1 to 2026 of 1 minus 1 over y squared all over p. And then since the Legendre symbol is multiplicative, we showed that earlier, this is equal to the sum from y equals 1 to 2026 of y squared minus 1 over p times 1 over y squared all over p. So how can we simplify this current sum? Yeah, so remember that the Legendre symbol finds quadratic residues. So 1 over y squared is obviously a quadratic residue. We already wrote it as a square. So 1 over y squared over p is equal to 1. So this is just sum from y equals 1 to 2026 of y squared minus 1 over p. And note that y squared minus 1 over p is negative our initial expression. Our initial expression was 1 minus y squared over p. So once again, using the multiplicative property of the Legendre symbol, we can factor y squared minus 1 over p as negative 1 over p times 1 minus y squared over p, right? And the sum from y equals 1 to 2026 of 1 minus y squared over p is equal to s. So this expression is equal to the Legendre symbol of negative 1 times s. So what is negative 1 over p? Do we know that? Remember, p is equal to 2027. So negative 1 over p is asking, is negative 1 a quadratic residue mod 2027? Yeah, it's not. as we showed last week, the -1 is only a quadratic residue of primes 1 mod 4, and 2027 is 3 mod 4. So -1 over p is equal to -1. Hence, from our expression on the previous slide, we have s is equal to -s, which means, of course, that s is equal to 0. So putting it all together, our total number of solutions is 2028 plus s, which is just 2028. Are there any questions? Well, if not, we're going to take a short 5-minute break. And when we return, Aditya will talk about more questions involving quadratic residues.
Okay, so let's get back to quadratic reciprocity. So another thing you might have wondered is when 2 is a quadratic residue. So the quadratic reciprocity theorem that we stated before, that's for odd primes, but we can actually say precisely when 2 is a quadratic residue. So that should say 2 over p. That's a typo. But so 2 over p is equal to -1 to the power of 1/8 times p squared minus 1. So we're not going to say the proof today. It's in the handout. We just don't have time for it today. So in particular, if we just look at this, this means that 2 is a quadratic residue when p is 1 or 7 mod 8, and it's a quadratic non-residue when p is 3 or 5 mod 8. So does anyone have any questions about this? Okay, so if not, we'll go to our next problem, which is this. Okay, so let's get started. Like the first natural thing to do here would be to just let 15a plus 16b be x squared and 16a minus 15b be y squared. So now we have two equations with a and b. So we can solve for a and b in terms of x squared and y squared. Can someone type in the chat what a and b are? Yeah, so we're just, like, for example, you can multiply the first equation by 16 and subtract 15 times the second equation um, to get b, and you can do something similar for a. So you get a is 15x squared plus 16y squared over 481, and b is 16x squared minus 15y squared over 481. So so now we need to know what x and y are, and so we want to find the minimum possible value of a plus b, and here a plus b will be 31x squared plus y squared over 481, but we still don't know anything about x and y other than that we have a and b are both integers. So that means that 15x squared plus 16y squared over 481 is an integer, and 16x squared minus 15y squared over 481 is an integer. So like, what modular congruences can we write from these equations other than what I just said? Maybe try to look at the prime factorization of 481. Okay, well, remember that 481 is 13 times 37. So yeah, so we can write, for example, 15x squared plus 16y squared is 0 mod 13. And if we simplify this a little bit, we can write this as 2x squared minus 3y squared is 2x squared is equivalent to negative 3y squared mod 13. But notice if we multiply by the inverse of 2 mod 13, which is 7, then the left side becomes x squared, and the right side, after some calculation, becomes 5y squared mod 13. Um, so now we have like this equation here, and if like, one idea we might have is try to move x and y so that they're both on the same side. So that would be by like dividing by y squared. And we can only do this when 13 doesn't divide y. So let's just assume that 13 doesn't divide y for now. And now we can write this as x over y squared is 5 mod 13. So if there do exist x and y that satisfy this, then 5 has to be a quadratic residue. So now the question is, does this agree with the result from quadratic reciprocity? And we can verify this pretty easily. So 5 over 13 times 13 over 5 is negative 1 to the 1/4 times 12 times 4, which is just 1. And note that 13 over 5 is equivalent to 3 over 5, and 3 is not a quadratic residue mod 5. So combining all of this, we see that 5 over 13 is actually equal to negative 1. So 5 is not a quadratic residue, which means that we couldn't have divided by y squared above. So that implies that 13 had to divide y. And if we look at that equation again, like x squared equals 5y squared mod 13, we see that 13 also has to divide x. So we have 13 divides x and y. So now let's try to see if we can do something similar with mod 37. So we have 15x squared is equal to negative 16y squared mod 37. So if we multiply by the inverse of 15, which is 5, this comes out to x squared is equivalent to negative 6y squared mod 37. So if we assume that 37 doesn't divide y, then that means that negative 6 has to be a quadratic residue. But so let's see if this is the case. First, because this function is multiplicative, this is negative 1 over 37 times 2 over 37 times 3 over 37. So can someone say what negative 1 over 37 is? Right, so 37 is 1 mod 4, so negative 1 is a quadratic residue. How about 2 over 37? Yep, so 37 is 5 mod 8, so by the results a few slides ago, we see that 2 is not a quadratic residue. So the last thing is to evaluate 3 over 37, which is pretty simple because we can just use quadratic reciprocity. So 3 over 37 times 37 over 3 is negative 1 to the 2 times 36 over 4, which is 1. And 37 over 3 is equivalent to 1 over 3, and clearly 1 is a quadratic residue, so that means that 3 over 37 is also equal to 1. So now if we multiply using this bullet here, it turns out that it's 1 times negative 1 times 1, which is negative 1. So this is not a quadratic residue. So we have the same thing as before. 37 has to divide x and y. So like altogether, 481 has to divide both x and y. And using the formula on the previous page, we can see that a plus b is minimized when x and y are both 481 because, well, we saw that a plus b was 31 times x squared plus y squared over 481. So it's clear that we want to minimize both x and y. And then if we evaluate this, it's 32 times 481, which is 392 mod 1000. So does anyone have any questions about this? Okay, so I guess we'll move on. So we saw that the Legendre symbol was multiplicative on the top, but it would be a little bit more like powerful if we could also extend it so that it's multiplicative on the bottom. And by this, I mean if we could have some symbol that would satisfy a over mn is equal to a over n times a over m. And so this is what's called the Jacobi symbol. And in general, um, so a few interesting facts about it. Well, a few important facts are that a over n is 0 when the GCD is not 1. This is a over n should equal b over n, that's a typo, when a equals b mod n. And also if we use this fact that it's multiplicative on the bottom, we can really define it as a product of these Legendre symbols that correspond to the prime factors of n. So we can write it as like a over p1 to the e1 times a over p2 to the e2 dot 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 a over pk to the ek. And the reason this is useful is that we can restate quadratic reciprocity using this. And so here we just have, if there's like odd positive integers that are relatively prime, m and n, then m over n times n over m is equal to -1 times -1 to the power 1/4 times n minus 1 times n minus 1. And also -1 over m is -1 to the 1/2 times n minus 1. And 2 over m is -1 to the 1/8 times m squared minus 1. Yeah, I can go back one slide. Okay, so as I was saying, like the reason this is like really useful is that now like quadratic reciprocity is not just limited to like odd primes. It's this form makes it much more powerful, but there is a warning here. Now the Jacobi symbol does not necessarily detect quadratic residues like the Legendre symbol. So like if a over m is -1 and a over n is -1, then since for our Jacobi symbol, a over mn would be equal to 1. But like, for example, I could say that like 2 is not a quadratic residue mod 3 and 2 is not a quadratic residue mod 5. So you would expect it not to be a quadratic residue mod 15. But the Jacobi symbol is actually equal to 1. So it's important to note that this does not actually necessarily mean that A is a quadratic residue mod Mn if you use the Jacobi symbol. So with that, we'll move to one final problem about quadratic reciprocity. Okay, so let's get started. So here we essentially just want to find a function that's equal to the Jacobi symbol. And like one idea would be to try to use quadratic reciprocity in some way. So does anyone have any ideas for how we can do that here? Because we don't really have any conditions on the value of A. So try to think about the the Jacobi form of quadratic reciprocity. So we want to apply it for odd positive integers m and n. So is there some way that we can make A odd? Yeah, so since this is multiplicative, we can always remove like powers of 2 from A. So by that, I mean if 2 to the k is the maximum power of 2 that divides A, and A is equal to 2 to the k times A1, then A over P is equal to 2 over P to the k times A1 over P. So really it looks that we can simplify this so that we can apply quadratic reciprocity by taking casework on the value of k. So let's do exactly that. Let's start with k equals 0. So that means that A is just odd. And if A is odd, then we can just apply quadratic reciprocity like normally. But first, we have to figure out what P is mod 4 so that we can simplify the quadratic reciprocity. So first, we had that P is A squared plus B squared. And if A is odd, then then B squared is either 0 or 1 mod 4. So A squared plus B squared has to be 1 or 2 mod 4. But since P has to be an odd prime number, that means that B squared has to be 0 mod 4, so that P is 1 mod 4. So then if we just apply quadratic reciprocity, we get that A over P is equal to P over A times -1 to the 1/4 A minus 1 times P minus 1. And A minus 1 is divisible by 2, and P minus 1 is divisible by 4. So that whole term goes to 1. So we just get A over P is equal to P over A. But recall that P is A squared plus B squared. So this is A squared plus B squared over A. And remember that we can, if we look at the top part, we can just take it mod A and it will be equivalent. So since A squared is divisible by A, we can reduce that to just B squared over A. And B squared over A is obviously equal to 1 because B squared is a perfect square. So B squared has to be a quadratic residue. mod A. So that means that A over P is always equal to 1 in this case. So that means that when A is odd, we can just set S of A equal to 1 because we have no other condition here. So let's move on to when K is 1, and that's when A has 1 power of 2. So in this case, we set A equal to 2A1, where A1 is odd. So when we use the property that it's multiplicative, we're writing A over P equal to 2 over P times A1 over P. But to find 2 over P, we need to find what P is mod 8, and then we can use the result that we saw a couple of slides ago for when 2 is a quadratic residue. So can someone say in the chat what P has to be mod 8 in this case? Remember that A is divisible by 2, but not divisible by 4. So that means A is 2 mod 4. Yeah, so it's 5, and that's because A is 2 mod 4, so A squared has to be divisible by 4, but it's not divisible by 8, so A squared has to be 4 mod 8. And if A is even, we have to have that B is odd because P is going to be an odd prime. So for all the odd numbers, B squared is 1 mod 8. And so if we add that, we get the P is 5 mod 8. So that means that 2 is not a quadratic residue mod P. And now we can apply quadratic reciprocity with A1 and P, since they're both odd and relatively prime. So then we get A1 over P times P over A1 is -1 to the 1/4 A1 minus 1 times P1 minus, that should say P minus 1. So since P minus 1 is divisible by 4 and A1 minus 1 is divisible by 2, this is just equal to 1. And so then we can simplify A over P as 2 over P times A1 over P. And since 2 over P is -1, and from quadratic reciprocity, we saw that A1 over P times P over A1 is 1. So that also means that A1 over P has to equal P over A1. So then we can substitute that, and this becomes -1 times P over A1. And if we substitute the value of P, this is -1 times 4A1 squared plus B squared over A1, which is equal to -1 times B squared over A1. And B squared is clearly a quadratic residue, so this whole thing is equal to -1. So we saw that when A was 2 mod 4, we can set S of A equal to -1. So now in the case when there's more powers of 2, one thing that we saw is that when we were computing P mod 8, we saw that in the previous case, A squared is 4 mod 8, but in all the subsequent cases when K is greater than or equal to 2, we have to have A squared is 0 mod 8, and also B squared is always 1 mod 8. So then P is 1 mod 8, and that just means that 2 is a quadratic residue mod P. So then we can just use the same process that we've been using throughout this problem and apply quadratic reciprocity with A1 and P. So A1 over P times P over A1 is -1 times 1/4, -1 to the 1/4 times A1 minus 1 times P minus 1. That's also a typo. So since P is 1 mod 8, we can say that this is equal to 1. So then we can just write A over P is 2 over P to the K, and 2 over P is 1. And also A1 over P is equal to P over A1 from quadratic reciprocity. And if we substitute for P and take the top part mod A1, this whole thing is equal to B squared over A1, and B squared is a quadratic residue, so this is equal to 1. So whenever A is divisible by 4, we can let S of A equal 1. And so just to combine everything from this problem, the goal was to find the function S. So, so this is the function that works. S of A is 1 when A is 1 mod 2, -1 when A is 2 mod 4, and 1 when A is 0 mod 4. So does anyone have any questions? Okay, so I guess we'll move on, and Daniel will teach the next section.
Okay, so the next section of our class will be talking about, in short, VPs. The official name we have here is periodic valuations, but it's not terribly important. So to begin, suppose that we have a prime P and a positive integer n. And we want to know how many times P goes into n. Well, we define this quantity as the periodic valuation of n. We define it to be the largest integer k, such that p to the k divides n. So we want the largest integer k such that n is divisible by p to the kth power. So essentially, how many times p goes into n. And we denote this number by Vp of n. So for example, V2 of 96 is 5. 2 to the 5 goes into 96, but 2 to the 6th is not a factor of 96. So there are a couple of properties of VP with respect to addition and multiplication. So the simpler one occurs when we multiply two numbers, then their VPs add. The VP of the product of two numbers is just the sum of their VPs. Does anyone have any questions on why this is true? You just take the largest exponent dividing A and add it to the largest exponent dividing B. Another one is when we add two numbers, their VPs satisfy this inequality. The VP of A plus B is obviously going to be at least this should be a typo. VP of A plus B is at least the smaller of VPA and VP. You should replace max with min. Sorry about that. And actually, we have equality if the two VPs aren't equal. So if, for example, P squared divides A, but B is only divisible by P, then we can be sure that the VP of their sum is exactly 1. The reason the inequality comes is if we add two numbers of the same VP, say we add 1 and 3, which are both not divisible by 2, when we add them, we can get something that's divisible by 2. And this inequality is why we have it. So some other facts about VPs. You might have seen Legendre's formula before, which gives you the VP of n factorial. You might have seen this in the context of, say, math counts or AMC, where they ask you to find the number of zeros at the end of factorial. And in that case, you're going to want the V5. So does anyone have any questions so far? Well, let's move on then. So if you haven't seen VPs before, or Legendre's formula before, you can prove it as follows. So if we write n factorial as the product of these integers, well, each multiple of p in the product is going to contribute one factor of p to the VP of n factorial. So for each multiple of p, we increase the total count by 1. And the number of multiples of p in this product is just the floor of n over p. But if it's a multiple of p squared, it has another factor of p to give. For the first term, we took p from all of the multiples of p, but multiples of p squared will still have a multiple of p remaining. And then each of these will result in another increase of 1. And we keep on doing this, and we get this big sum. And this sum ends up being finite because eventually the floors are all going to be 0. So an alternate form for this formula is n minus spn over p minus 1. And we use spn to denote the sum of the digits of n in base p. So this is occasionally useful, and you can prove it by writing the base p representation of n. So ak times p to the k, and so on to a0. And then you can just verify this equality to just directly substitute everything in, and they should work out to be equal. And since we have the first formula, we also get the second formula. And the full expansion of this will be in the handout. Does anyone have any questions about this part? No questions? Well, then we can move on to our first example. So this is a fairly famous lemma, but the proof is also very important. So if we have positive integers satisfying these 3 conditions, so we're looking at an odd prime. This equation does not hold for p equals 2. P is not divisible by, it does not divide either a or b, but it divides their difference. So what this means is basically a and b are congruent mod p, but they're not both 0. Then when we want to find the VP of the difference of 2 powers of a and b, we can bring the exponent down and simply add the VP of the exponent to the VP of their difference. Does anyone have any questions with this statement of the lemma? So there is a form of LT when p equals 2, but in the end, it ends up being very similar to the difference of squares formula. So I personally don't know it, and I'm not sure it's super important. It should be fairly easy to rederive when you need it. Well, the proof of this lemma is fairly important, so you understand where the conditions come from. So does anyone have any ideas how we might approach such a statement? Yes, so the binomial theorem will be involved in this. But with the binomial theorem, it's quite hard to show that some number is divisible by exactly p to a large power, but not p to the large power plus 1. So in your own time, you might want to try just going straight binomial theorem. You'll find that it might be that'll be a little hard to work with. The hardest part will be to n choose some things. It's hard to control what these are going to look like. So in order to, but we do want to use a binomial theorem. We just don't know how to handle n. N is a very variable number that will screw up the the binomial coefficients involving n will screw up the terms in our sum. So what we're actually going to do is we're going to induct on VP of n. So the proof actually will consist of 2 steps. In the first step, we want to verify if the lemma when VP of n is 0. So that is when n is not divisible by p. And for the second step, we're going to verify that if the lemma works for n, then it works for p times n. And this, with this logic, we can build up all the exponent lemma for all positive integers. So let's deal with the base case first. If VPN is 0, then we want to show this. How might we go about doing this? We want to show that the VP of the difference of powers is exactly the same as the VP of the difference. Is there a helpful restatement we can make of this? Yes, the factorization will be nice here. But first, we can actually rewrite it in this way. P can't divide the quotient of the two. We know that their quotient is an integer because we can factor it. And since if we want to show the VPs are equal, we just have to show that the quotient's not divisible by n, by p. Does everyone see why this is true? If p divides both sides the same number of times, then when we divide one side by the other, we're not going to get any factors of p left. So now we want to show that p doesn't divide this the second factor. And this is nicer. Instead of having to handle VPs, which can be fairly abstract algebraically, we now have a concrete thing we want to show. Something is not divisible by p. So since we're going to use a hypothesis, p divides a minus b, now we know that a is equivalent to b mod p. In order to show that this factor on this side is not divisible by p, we're just going to consider it mod p. If we show that it's non-zero modulo p, then we'll be done. Does anyone have any questions with the proof so far? Well, let's continue with the base case then. So modulo p, we have this factorization. But since a is congruent to b, we can replace b with a everywhere. And when that happens, every term in the sum becomes a to the n minus 1. So it ends up being congruent to n times a to the n minus 1 modulo p. Is this first step understandable? We're using the condition p divides a minus b here. So modulo p, a and b look the same. So now we have that is congruent to n a into a to the n minus 1 mod p. How can we argue that this is not 0? Yeah, we can now use the two other hypotheses we had. So we haven't actually used the hypothesis P is odd, but we can use the second bullet. P doesn't divide A, and we already used the third bullet. So by assumption, P doesn't divide N. This is our base case. And also P doesn't divide A. This is a hypothesis of the lemma. So that means P can't divide the product of N and A to the N minus 1. So the left-hand side we have here isn't divisible by P. It has a non-zero residue. So that completes the base case. Does anyone have any questions about the base case? Okay, then let's move on to the inductive step, which will be a bit more involved. So for the inductive step, suppose the lemma holds when the VP is equal to K. Then we want to show it's true when the VP is equal to K plus 1. So now if the VP of N is K plus 1, let's divide out one factor of P. So that means when we divide out one factor of P, the VP goes down by 1. And when it goes down by 1, then we can use the inductive hypothesis. So we have the definition of the variables here. Now if we pull the inductive hypothesis, we know that we can lift the exponent here. And now we want to relate it back to n, the small n. So now small n is equal to P times big N. So the inductive hypothesis tells us the second to last bullet. And we want to prove this bullet. So how might we go about doing this? We have the second to last bullet as an assumption, and we want to prove the last bullet. Yes, we can do a factorization. So since we can take a look at the left-hand side in the final expression. It's the difference of pth powers. It's the pth power of a to the n minus the pth power of b to the n. And we have a to the n and b to the n in our inductive hypothesis. So somehow we can handle that. So actually, if we subtract the two equations, this is what we want to show. We're just subtracting now it's third to last bullet from the second to last bullet. And now if we can show that this equality is true, then the inductive hypothesis follows. Is this step clear? Well, let's move on. So if you take a look at the right-hand side here, well, the VP of Pn is going to be one more than the VP of n. It has exactly one more factor of P. So it's just one. So this is what we want to show now. And this is quite good. We want to show that the VP of something is 1. So we have to show that it's divisible by P, but not P squared. And if we look at our fraction, it's a difference of powers. So we can factor it. First, let's put our hypotheses to use. Since P is divisible by a minus, if P divides a minus B, it also divides a to the n minus b to the n. So that means a to the n and b to the n are congruent mod P. So in order to use the binomial theorem, we're going to have to assign some variables. So now we can let b to the n equal m, and a to the n equals m plus a multiple of P. Now, by our hypothesis that P doesn't divide B, we know that P doesn't divide M. And now we're going to want to substitute into the expression. When we do that, we want to show that this expression on the right-hand side is divisible by P, but not P squared. So how should we go from here? We want to show that the expression is divisible by P, but not P squared. Well, as mentioned earlier, we can use the binomial theorem. So if we expand the thing with the binomial theorem, we get this, and it simplifies to this. So now we want to first argue that it's divisible by P. Why is this divisible by P? Can someone argue why this expression would be divisible by P? Yep, every term in here is divisible by P. Well, no, all of them are divisible by P. That's why it is, the P choose one here is divisible, makes it divisible by P. So all these terms have a factor of P in them, and then this guy has a factor of P choose one, which is P as well. So it's immediately divisible by P. Now, how can we argue it's not divisible by P squared? Well, starting from the third term over here, all the terms have a factor of P squared. So all of these are divisible by P squared. The second term actually also happens to be divisible by P squared. You have one factor of P from Pk. But then P also divides P choose 2. If P is odd, this doesn't work when P equals 2, which is why this statement of lemma requires that P is odd. But if P is odd, then P divides P choose 2. So the second term is also divisible by P squared. But the first term is not. P choose 1 is just one factor of P, and P isn't a divisor of M. So there's only one factor of P in the first term. Now all of the terms are divisible by P squared, except for the first term. That means the entire sum is not divisible by P squared. So we've shown that this thing is divisible by P, but not P squared. So we're done. Any questions? Well, let's get on to a down-to-earth application. Why can't P choose 2? PP2? So let's see. Which bullet was it? The second to last bullet. We use the hypothesis that P divides P choose 2. This is only true if P is odd. And yep, for the sum of powers, whenever n is odd, you can just write a to the n minus negative b to the n. Yeah. But if n is even, then there's no general formula. Well, let's move on to computation application. So a problem from this year's Amy. Give you a little time to look it over. Yep, so we have a difference of powers, of nth powers, and we want them to be divisible by large prime powers. So LTE seems like a good example for this, a good choice for this one. So let's start by calculating the V3 of this thing. Well, the first thing we'll want to do is check the hypotheses. 3 is odd, which is good. 3 doesn't divide 149 or 2, which is good. And 3 divides 149 minus 2. So all 3 hypotheses are fulfilled, and we can use LTE. Let's throw it straight into the formula. So the V3 of 149 to the n minus 2 to the n, we can lift the n out. That's V3 of 149 minus 2 plus a V3 of n. Now you can just calculate that the V3 of 147 is 1. So that's V3 of n plus 1. Now we want the difference of powers to be divisible by 3 cubed. That means the V3 of this thing should be at least 3. Since V3 of n plus 1 is at least 3, then we know that V3 of n is at least 2. So 3 squared is a factor of n by the definition of V3. Any questions on this first step? Well, let's move on to 7. Again, check the hypotheses. 7 is odd. 7 isn't divisible by 149, isn't a divisor of 149 or 2. And 7 divides their difference. So we can use LTE on this one. Again, throw it straight in. We get it V7 of 149 minus 2 plus V7 of n. And you can check that V7 of 147 is 2. So that's V7 of n plus 2. Now, if we want the difference of powers to be divisible by 7 to the 7, the V7 of the difference has to be at least 7. So V7 of n from LTE is at least 5. And now 7 to the 5 divides n. Any questions on this step? We did essentially the same thing with V7 as V3. So 2 primes down, 1 to go. Now let's use LTE on 5. But we can't. It doesn't satisfy the hypothesis 5 divides 149 minus 2. Actually, so the reason we have the hypothesis P has to divide 149 to the n minus 2 to the n is because otherwise the difference isn't even necessarily divisible by P. So we don't actually always have 5 dividing 149 to the n minus 2 to the n. But for which n is the difference of powers a multiple of 5? I see we already have an answer in the chat. So you can, we'll simplify this modulo of 5. So 149 is congruent to 4 mod 5. So 4 to the n minus 2 to the n mod 5. And then we can factor out a 2 to the n. So now if the difference of powers is divisible by 5, then 5 has to divide 2 to the n minus 1. 2 to the n is not going to be a multiple of 5, so it has to be the other factor that provides the 0 mod 5. And you can check, we had a discussion on orders last week, that this occurs exactly when n is divisible by 4. So now this automatically tells us that n has to be divisible by 4 as well. So let's set n equals 4 times k. where k is a positive integer? Well, we don't just want 5 dividing the difference. We want 5 to the 5 to divide the difference. So let's use LTE. We can get the restriction 5 has to divide a minus b by writing the difference of powers like so. It's a difference of the kth powers of 149 to the 4th and 2 to the 4th. So when we put this into LTE, how we use the exponent k, we have the hypothesis 5 divides 149 to the 4 minus 2 to the 4 fulfilled. So we can use LTE. And if you do a little bit of work, say just factoring the difference of 4th powers a couple of times, you can check that the V5 of this thing is 1. So V5 of 149 to the n minus 2 to the n is going to be V5 of k plus 1. And V5 of k equals V5 of n because they just differ by a factor of 4. So if we want the V5 of the difference of powers to be at least 5, then V5 of n is at least 4. So n is divisible by 5 to the 4. And we've now gotten every single condition we can get on n. Any questions before we begin the final step? Well, now let's just call it our conditions. So we know that n has to be multiple of 3 squared, 7 to the 5th, 4, and 5 to the 4th. So now n has to be divisible by their product. These are all prime powers. So we get 2 squared times 3 squared times 5 to the 4th times 7 to the 5th. What we want to find is the fewest possible number of divisors of n. And this is clearly minimized when we choose n equals 2 squared times 3 squared times 5 to the 4th times 7 to the 5th. If we choose any multiple of it, then it's going to have strictly more divisors. So we just count the number of divisors of this thing, 2 times 1, 2 times 1, 4 times 1, 5 times 1, and we get 270. Any questions? If not, then we'll have Brian discuss the final problem of the day.
All right, so here's the last problem of the day. And then I'll give you guys some time to like read it, think about it, and then we'll be going over it shortly. Okay, so well, one thing that we noticed about this problem is that we have a lot of powers of 2 on the right hand side. So then this motivates us to try to factor out these 2's, right? And then so we factor out these 2's, and then so we can write it in this form, and then we group all the 2's together. So then we get 2 raised to some big power multiplied by a bunch of odd numbers, right? So then this tells us that if we take the V2 of it, then that's just the exponent n times n minus 1 all over 2. Right, and then so well, because the V2 of the right hand side is n times n minus 1 over 2, that means that the V2 of the left hand side is also n times n minus 1 over 2. Right, but we know information about like what happens when we take the V2 of a factorial, right? When we take the v2 of a factorial, it's essentially just k minus the sum of the digits of k in base 2, right? And this is at most k, because the sum of the digits is non-negative. So well, this actually gives us a bound on k. K is at least n times n minus 1 over 2, right? And then, well, what does this mean? This means that basically the left-hand side is going to be quite large, and then it's possible that it will eventually become too large for the right-hand side, right? So, well, okay. So, well, I guess, so what would be something that we would want to do? Well, we can, well, we can do some bounding, right? Because k factorial is clearly at most n times n minus 1 over 2 factorial. And then just because k is at least n times n minus 1 over 2. And then, well, what does this mean? Well, we now just try bounding the right-hand side, right? Well, the right-hand side, if we were to just replace everything, like if we were just to remove all the subtraction signs, essentially, then we can get a cleaner bound of 2 to the n squared, right? So, well, basically, we have 2 to the n squared is at least k factorial, and n times n minus 1 over 2 factorial is at most k factorial, right? So we can get this bound. And, well, if we look at it, this is like not true for large n, right? Because essentially, like, the left-hand side, we only like if we have a bunch of numbers, there's n squared of those numbers, and they're all 2. Whereas with the right-hand side, we have about half n squared numbers, but then like most of them are a lot larger than 2, so then the right-hand side will eventually become greater than the left-hand side, right? So, well, we can prove this with induction. So we claim that actually large n is just n is at least 6 is enough. So, well, first, I guess we will prove it for n equals 6. We have 15. We want to show that 15 factorial is greater than 2 to the 36. Well, we can just do this by like bounding the values, like 15 factorial. The first 7 values make up 7 factorial, and then the next 8 numbers are greater than 8 to the 8. And then 8 to the 8 is equal to 2 to the 24, and 7 factorial can be calculated to be greater than 2 to the 12. And then, so that's 2 to the 36, which is what we want, right? So that's enough to prove our base case. And now for the inductive hypothesis, for the inductive step, we assume the inductive hypothesis, which is that n times n minus 1 over 2 factorial is greater than 2 to the n squared, right? And then the inductive step, we of course want to show that the same is true for n plus 1. Right, so how would we do this? Well, we can first express n times n plus 1 over 2 factorial as n times n minus 1 over 2 factorial times, well, there's n terms between n times n minus 1 over 2 to n times n plus 1 over 2, and then they're all greater than n times n minus 1 over 2. So then this is, so that's how we get the first inequality, and then the second inequality follows from the inductive hypothesis. So, well, if we can show that this last inequality is true, then we can be done, right? So, well, we can simplify this by canceling out 2 to the n squared. And then we can simplify this some more by taking an nth root. And well, basically, because we already have n is at least 6, the left-hand side is at least 15, and the right-hand side is less than 8, right? So then that's enough to prove the inductive step, right? So now we have proven the inequality that we want, right? But we remember that if k and n satisfy it, then we also need essentially the reverse inequality to also hold, right? But we can't have them hold at the same time, so we can't have n is at least 6, so we have to have n is at most 5. Right? And since now there's only 5 values left, we can just check all 5 of them. And then so we'll just do that. So n equals 1, we can check just is k equals 1. N equals 2, give k equals 3. N equals 3 gives 168, and 168 is not the factorial of any number. And then n equals 4 gives 20,160, which is also not the factorial of any number because it's between 7 and 8 factorial. And then n equals 5 is also not a factorial because basically we have, for example, 31 dividing the right-hand side. But then if 31 were to divide a factorial, all smaller primes would have to divide it, but then 29, for example, doesn't divide it. Right, so this is why n equals 5, for example, doesn't work. And then so that's all the cases. Right, so then we just have that it's 1, 1, and 3, 2. And that's all.
Thanks to everyone for attending. That's it for today. We'll send out an email for next week's registration closer to the date.